Hey guys, okay, this is a shorter topic. We're going to talk about the health effects of nuclear radiation. And the main problem with nuclear radiation is the fact that it is what we call ionizing radiation. So the particles and gamma rays that are emitted, they can ionize atoms. They can remove electrons from atoms. So that can cause some problems when you're absorbing this radiation into your tissues and atoms are becoming ionized. You can have, with really large doses, you can actually have radiation burns. You can cause definite damage to the tissue almost immediately. But in lower levels, the ionization can cause cellular problems, so cells may not operate correctly. You can get rapid growth of cells, cancers, or you can get cellular death. So certain cellular operations are interrupted. So that's the main cause of potential health effects, is the ionization capability of this radiation. All right, with that being said, we're going to introduce some quantities, relative quantities that are used. And the end goal here is to try to get some handle on potential health effects of the radiation. So I want you to consider that little cube there. That represents some tissue, biological tissue. So the first quantity that we worry about is what's called the exposure. So I'm indicating that this is simply the amount of radiation that is going to be incident on that tissue. So that is called the exposure. We'll say more about that in just a few seconds. Then the next thing that happens is the radiation, some of that radiation is going to be absorbed. So our focus now is on what's called the absorbed dose, the amount of radiation that's actually getting absorbed. But that is not the end of the story, because then what you have to worry about is what type of radiation was absorbed. So this forms what's called the equivalent dose, or sometimes we'll hear it called the dose equivalent. And the way we figure this out is we take the absorbed dose and we multiply that by what's called a relative biological effectiveness factor, or RBE factor. And this is a pure number, and the size of that number depends on two things: what type of radiation is absorbed, but also what's the energy of that radiation. Because the more energy in the radiation, the more potential damage it can cause. So these are typical values. Gamma rays are typically not as dangerous as betas and alphas once they're in your body. And that's a big caveat. So they're going to have RBE factors of around 1. Beta particles, both minus and plus, are going to have RBE factors between 1 and 2, depending on the energy. Alpha is 10 to 20. Okay, so when you look at this table right here, you say, oh, it looks like gamma rays are not that dangerous compared to alphas. And that is true if all three of these are absorbed in your tissues. The issue with gamma rays, though, is gamma rays are relatively easily absorbed. Okay, alphas are not. Alphas are so big that even if you're exposed to alpha radiation, the chance of the alphas actually getting into your tissues is very, very low. Any sort of barrier is effective at pretty much absorbing alphas, even a thin piece of tissue paper, as textbooks like to say. So now, if you actually ingest and get alphas into your tissues, then yes, they are the most dangerous. But that's why you may hear that the biggest, most of the radiation effects that people worry about are from gamma radiation, only because you're much more likely to absorb gamma radiation than alphas. However, if you have alphas ingested, and this could be actually usually through breathing into your lungs, then alpha radiation can be extremely potentially damaging. Okay, so you may have heard about radon as a potential cancer-causing agent. Radon gas can be breathed in by people, and then that radon is an alpha emitter, and it gets inside your lung tissue where it can cause damage. So some homeowners are worried about the amount of radon that they have around their homes. It's normally more of a concern when you have basements where you're underground and you have radon sources in the ground. Although the damage caused by radon gas is not as great as you first might think. It was in the news about 20, 30 years ago, and people are still a little bit concerned about it, but it doesn't seem to be as big of a factor in lung cancers as people might have first thought. There's a lot of literature on the internet you can read about radon gas and lung cancers. Okay, let's continue then. I'm going to call up this table. So here's where we're going to describe these three quantities and give their units. So the exposure, this is the amount of ionizing radiation you're exposed to. So we're focusing on nuclear radiation, but X-rays that come from atomic transitions. X-rays are also an ionizing radiation that you have to be careful with. Okay, so the SI unit is Coulomb per kilogram. You guys don't have to memorize this. I'm just going through it because it's interesting information. So you can see it's charge per mass. So the way you define the, I should say measure the quantity, the exposure, is you see how much charge is produced by the ionization. So the ionized charge is going to produce so many coulombs, and you look at that per mass of absorber, per kilogram. The common unit for that, in addition to the SI units, there are common units. They're more historical, but again, they're commonly used, is the Roentgen. And the conversion factor is right there. 3876 Roentgen in 1 coulomb per kilogram. Okay. Now, the absorbed dose, the amount that gets into your tissues, this is the SI unit is the gray, GY. The common unit you may have heard of is the RAD, which stands for radiation absorbed dose. And there's a factor of 100 difference. 1 gray is 100 rads. Okay, so the absorbed dose is the amount of radiation absorbed by the tissues. And then once you multiply the absorbed dose by the RBE factor, that number, you form what's called the equivalent dose. And the SI unit officially is the sievert, SV. The common unit is the REM, which is an acronym for Roentgen equivalent in man. If interesting tidbit. And again, there's a factor of 100. 1 sievert is 100 REMs. Okay, so what's important in determining the health risk is what is the equivalent dose, but also what type of time are we talking about? Did you get this equivalent dose in 2 hours, in 2 weeks, in 2 years? So the equivalent dose and the duration of the dose are the most important quantities in determining the health risk. Where you get this equivalent dose is also a factor, but probably the biggest two are the dose and the duration. Okay, just some numbers that you can look at on this slide. What's the average annual natural background level of radiation? And it's around 300 millirem. And that's going to be coming from, again, natural sources. About 2/3 is from thoron and radon in our Earth. 1/3 is from other terrestrial sources. So other isotopes in the Earth. And also we have cosmic rays coming from the sun. Okay, and also inside of you, you actually have radioactive isotopes. The most abundant is potassium. I think it's potassium 40. I can't remember, but there is an isotope of potassium that is radioactive. So it's not that we're not used to radioactive isotopes in nuclear radiation. We are exposed to nuclear radiation all the time, even have some sources inside our bodies. It's when you get very large dose equivalents in a short amount of time where you have a higher risk. There is an artificial background level that we're all exposed to, or can be exposed to, I should say. And that again is around, on average, about 300 millirem. And that's mainly for medical procedures that are using X-rays, okay, like CT scans and or PET scans that use a radioactive tracer, okay. So they're about the same amount. Now, what are recommended limits beyond background? It's roughly 100 millirem for the general public in a year. And if you have a special occupation, like you're a uranium miner or nuclear power plant worker or work with nuclear medicines that are used to either treat cancers or for imaging, it's around 5,000 millirem, okay, for occupational limits. And these numbers are coming from the Nuclear Regulatory Commission. You can go to this link if you'd like to. Okay? All right. So that's it. Just be familiar with these terms and these limits. And I could ask you a question about these on the last test. Okay? All righty. Bye-bye.